Good afternoon, everyone. I would like to start by thanking the organizers for inviting me to give this talk. It required me to, go beyond and explore, read about areas in which I am directly not working at present. So it was a very rewarding experience for me. So I will be talking about the future goals of neutrino physics, and this is really very diverse. The landscape is very diverse. This is the ICTS from web page I saw, and this is the thing. So I will start with what we know about neutrino properties. So neutral leptons with 3 flavors. Flavor eigenstates are not same as the mass eigenstates, and they mix among each other, which leads to neutrino oscillations, which have been observed. Now, mixing between flavor states is governed by the PMNS matrix. And the mass splittings and mixing angles are measured, and there is a limit on the sum of neutrino mass from cosmology. Now, what we don't know about neutrino properties, first of all, oscillation experiments give us the mass splittings. We don't know the absolute masses. We don't know the nature of neutrinos, that is whether they are Dirac or Majorana. Are there more than 3 flavors? For instance, if there are sterile neutrinos, we need more precise measurement of mixing angles. Can we test unitarity of the UPMNS? Then mass ordering and CP phases. Also, we don't know about the origin of neutrino masses and mixing at a fundamental level, although there are many models. Also, there are a lot of BSM physics, like if neutrinos have non-standard interaction, do they decay? Is there violation of fundamental symmetrics like CPT, Lorentz invariance, and it goes on. So there are many things about neutrinos that we know, and there are many things that more things that we don't know actually. So this is a picture of neutrino sources and experiments, and that gives us an idea about the vastness of the landscape. So the neutrino energy goes from 10 to the -4 to 10 to the 18 electron volt. Here we have the very low energy Big Bang neutrinos till the very ultra high energy neutrinos. And these are the various experiments that have been done, that have been planned to explore this energy range. This is the cross section. So you can see that at this end cross section is very low, whereas here cross section is high, although the flux is low. So I will start with neutrino oscillations. We have evidences for neutrino oscillation from solar neutrino experiments, the famous charge current to neutral current ratio of the Sudbury Neutrino Observatory, which proved the solar neutrino oscillations. Atmospheric neutrino experiment, the zenith angle dependence in the super K data, the reactor neutrino experiment, the neutrino oscillations observed in Camland, and in accelerator, this is MINOS, neutrino oscillation observed in MINOS using accelerator. We also have results from T2K and NOVA. So the 3 neutrino paradigm is well established from all these experiments. So this 1-2 sector is governed by the solar plus Camland data, and the 1-3 mixing angle has come from reactor experiments, and the delta m squared 3-1 and the mixing angle θ2-3, these are primarily coming from the atmospheric and long baseline experiments. And because θ1-3 is non-zero, you can see that there is interplay among different sectors, and the 3 neutrino states can be arranged in 2 ways, where the third state can be higher than the first 1 and 2, or it can be lower, giving us the normal and inverted mass ordering. And these parameters, all these parameters have been, non-zero values have been discovered and measured with sufficient precision, but the future is what we don't know. And what we don't know is, one is whether the mixing angle θ2-3 is in the first octant or second octant. Right now, there is a preference for the second octant. We also don't know the ordering, although right now there is a preference for the normal ordering. And delta CP plus 90, we know, is disfavored at more than 3 sigma, irrespective of the mass ordering. So these plots, if one sees, then it will show that, the best fit, for instance, in the for θ2-3 here in the second octane. This is, but the significance is very less. So oscillation experiments are not sensitive to the Majorana phases. They are also not sensitive to the absolute masses, as I have said earlier. So now I go to the future. So the immediate goals are determination of hierarchy, octant, and CP phase. There are also studies on synergy between different experiments. There is some indication of a sterile neutrino, so that signature of sterile neutrino. There are also certain ongoing activities, precise measurement of neutrino cross sections, which are very important for getting precision values of oscillation parameters, for instance, nature of neutrinos, absolute neutrino mass. Then probing new physics in oscillation experiments. So physics like non-standard interaction or sterile neutrino can affect the oscillation. There are some emerging goals which are like search for dark matter in neutrino facilities, probing BSM physics through new interactions in neutrino facilities, and neutrinos and multi-messenger astronomy. So I will try to cover as much as possible. Otherwise, my slides are there if anyone is interested, if I cannot finish. So there are many these are the snapshot of current and future experiments. So there are many future experiments like, for instance, T2HK, Juno, and atmospheric Dune, then atmospheric experiments like ice cube upgrade, and then Hyperkamiokande. So these experiments are going to give us the information on hierarchy, delta CP, and mass ordering. So the salient feature of the long baseline experiments, as we have, so these are mostly less than 1,000 kilometers, excepting Dune, which is 1,300 kilometers. And what we have done is we have gone to high intensity beams and bigger detectors. And these are the atmospheric neutrino experiments, and there are water Cherenkov, liquid argon, and magnetized iron. I know there will be a separate talk, so I won't talk much about it. So the atmospheric neutrinos, as compared to long baseline, the matter effects are important because they pass through a large distance in the Earth. So the first goal is to determine the mass hierarchy, and it can come from matter effect in large baselines and interference effect in vacuum oscillations. That's what Juno is aiming to do. Also, there is some sensitivity from absolute neutrino mass measurements, neutrino-less double beta decay, and cosmology. So to start with, Juno is a reactor anti-neutrino experiment. This is a 20 kiloton liquid scintillator detector. And the detector is, there are two sources, and this is at around 53 kilometers from the two reactors. So this is the position. So it is, at the minima of the survival probability, which is actually important to understand the physics. And it is 2023 mid. That is the expectation to complete the detector. Its goal is determination of mass hierarchy firstly, then precision of oscillation parameters. It can also detect solar, supernova, atmospheric, and geoneutrinos, and can do different physics with that. So the hierarchy sensitivity in Juno comes because of the interference of the, I have two mass squared difference, delta m squared 3.1 and delta m squared 2.1. And it comes from the interference term, and there is a term, usually we have sine squared delta 3.1. So there is no, if we take, for instance, 2-generation picture, but if we include the 3-generation effects, including delta 2.1 and theta 1.3 both as non-zero, then there will be a term which will have hierarchy sensitivity. And this is the plot, like, normal ordering and inverted ordering, blue and red. So you can see there is a slight difference in the frequency. So to detect that, one needs better than 3% energy resolution. And Juno can give 3 sigma hierarchy sensitivity in 6 years. It is also can determine the oscillation parameters at sub% level, like delta m squared 3.1, delta m squared 2.1, and sine squared theta 1.2. I want to mention that the first study on a 60 kilometer baseline experiment was done by us back in 2003, where we showed that the precision of theta 1.2 is very high in such an experiment. Later on, this kind of work was done by this group to show that 60 kilometer experiment also has a very good hierarchy sensitivity. So there is also a lot of effort on studying the synergy between different experiments. As I said, the atmospheric neutrinos are sensitive to the matter effect, whereas Juno is interference effect in vacuum. And this paper was done where a Juno plus ice cube upgrade or Pingu combined analysis was done. So you can see this black line is the Juno sensitivity, blue line is the ice cube sensitivity hierarchy, and combined is the sensitivity if I combine Juno plus ice cube. So one can see that because the probabilities behave differently in these two experiments, one can get some synergy, and which is important for enhancing the sensitivity. A similar study has been done for the determining the delta CP. So here is some plot which is for T2K plus NOVA plus INO, which we did in 2013. And what it is showed is this green line is the T2K plus NOVA sensitivity. This is sensitivity to delta CP discovery, whether delta CP is different from 0 or 180. And what you can see is that this green region is even below 2 sigma. But if we add INO to it, like this is the INO 3D analysis, which takes into account hadrons, then it touches the 3 sigma level. So why this happens is because this INO has a very good hierarchy determination capability. And because of that, in this region, INO helps to remove the wrong hierarchy, wrong delta CP regions, which T2K and NOVA cannot remove because they are not sensitive to matter effects. Similar study has been done also for Hyper-K using their atmospheric data and the T2HK, the beam experiments. And you can see that beam only is less, but if you consider the hierarchy atmospheric plus beam, then they get a better sensitivity for delta CP. So I will not talk about Dune because there is a dedicated talk to Dune. I just want to remind people that there is a near detector complex with 3 near detectors. And also this is a 1300 kilometer experiment. And it is good for delta CP and hierarchy. Bipul will probably talk about it. I want to talk about the impact of systematic uncertainty because it will relate to my next slide. So here, we see that the no systematics is so high. However, if you increase the systematics, then you can see your sensitivity decreases. So systematic uncertainties play a very important role for precision measurements, and near detectors help in reducing this. And precise knowledge of neutrino nucleus cross-section is very important for this. Which brings me to the neutrino interaction cross-section experiments. So this is a summary of many of the experiments. So the near detector beam of these beam experiments can help in this. There is also the short baseline neutrino experiment in Fermilab. I will talk a little bit about it during the sterile neutrino search, but this can also determine. Then there are dedicated experiments like Minerva, Annie, Ninja, and in LHC, the high luminosity LHC, the forward physics facility has the ability to determine the neutrino cross sections at very high energy. I will talk about that little bit. So I think the future efforts in this will be experimental measurement of neutrino nuclear cross sections and refinement of theoretical calculations, including many body effect, nuclear form factors from lattice QCD correction. Then there are strategies for event generators which needs to be developed because these are all crucial for precision neutrino measurements. Now I talk about the forward physics facility. So in LHC, the largest flux of pion, kaon, d meson neutrinos, they come in the forward direction. And there can also be BSM particles like dark photons, action-like particle like dark matter. And to detect all this, the forward physics facility has been proposed, and this has a very rich and diverse program. I don't know if you can see, it can do new particles, dark matter, astroparticle, neutrino. And in neutrino, the important thing is that it can do the laboratory measurements of neutrino at the TeV scale for the first time. Detection, so they can detect thousands of tau neutrino interactions, and the phasor detector in the far forward region running for 4 weeks have detected 6 neutrino events. So they are planning 5 detectors: phasor 2, phasor nu 2, Formosa, SND, and Flare. And you can see that many of which will be used for the neutrinos, emulsion-based and liquid argon-based. And the conceptual design report should be ready by mid-2023. So coming to neutrino interactions brings me to the coherent neutrino nuclear scattering, which has given wonderful result in 2017. So it is, so they detect the, this is detected by the tiny energy deposited by the nuclear recoil. It was proposed by Friedman in 1974, and it took so many years to observe this for the first time. And you know, the dark matter experiments were a motivation. And because it is challenging, because recoil energy is about 50 keV for 10 MeV neutrinos, but the cross section is very high, you can see. And this is the CNS experiment has done a 6.7 sigma discovery of this cross section, which is consistent with SM at 1 sigma. So there are a lot of physics studies that can be done in coherent, for instance, nuclear physics and nuclear form factors, precision SM test like weak mixing angles, BSM physics, non-standard interactions, neutrino magnetic moment, supernova neutrinos, because the cross sections at supernova neutrino energies one can calculate, and dark matter such. So this is a plot for the sterile neutrino sensitivity. This is the NSI constraint which Coherent has given. And they have also done an analysis in this work on probing sub-GeV dark matter with CSI at this neutrino spallation neutrino source. So these are the coherent bounds. So and these are the masses. So about 100 MeV, 10 MeV region. So the important thing here is to that, you know, you can test your BSM models through this coherent experiment. So the phase 1 is to observe this process with multiple detector technologies, and phase 2 is precision measurements with large detectors. So there are so many detectors planned, and these are their commission dates, and you can see that there are some larger volumes for precision measurements, larger mass for precision measurements. So I talked about neutrino oscillation, but let me now talk a little bit about BSM in neutrino oscillation experiments. In the sense, I mean BSM which affects the oscillation probabilities. So for instance, if I have non-standard interactions, then it can give rise to additional matter effect inside the Earth. Then there can be many other things like non-unitarity of neutrino mixing matrices, decaying neutrinos, etc. These are all subleading effect because the oscillation is the dominant effect that has been proved by the data. This changes the oscillation probability, and it will impact the 3-generation picture that we are using, because there will be extra parameters, BSM parameters, and this gives rise to a famous problem called degeneracy, which is if you have additional phases whose values you don't know, then you have spurious solutions. So one can also constrain new physics parameters, and I think the future goal here should be, because there are several BSM scenarios, whether there can be some unique signatures that we can find in these experiments. So I will just discuss only the sterile neutrinos. And sterile neutrinos actually can exist in all scales. We can have light sterile neutrinos, EV scale. We can have KEV sterile neutrinos, which are proposed for dark matter candidate. And we can also have very heavy sterile neutrinos, which are needed for our neutrino mass generation through seesaw. But here I am now talking about the EV scale sterile neutrinos. And that is because there are several experiments which have indicated that to explain their data, an EV scale sterile neutrino may have to be introduced. So first, this came from the LSND experiment in 2001. And so they observed nu mu bar oscillation. It was a 3.8 sigma signal, and the delta m square was greater than 0.2 EV square. Then mini-bone experiment was planned with a different energy range and different L, but the same L by E to test the LSND results. But mini-bone also reports some excess. And this is the LSND plus mini-bone plot. So this is the brown is the mini-bone and blue is the LSND. So the mass scale cannot be seen, but this is around delta m square 0.2, 0.3 V square, around that ballpark. But there are several other experiments which have not seen the sterile neutrino, seen such indications. So that makes the field little, the fits very constraining if one does global fits. And that makes also the field is still very alive, and one has to explain why certain experiments, which are mainly the disappearance experiments, which are not seeing the signal, and these appearance experiments are seeing. Another interesting thing in mini-boon was the low energy excess. So it found some excess event in the low energy, which could not be explained from the background. And they cannot actually distinguish between the Cherenkov cone between electrons and photons. So the SBN experiment in Fermilab was designed to test this. So they have a near detector, and there is microboon and Icarus, two detectors which has somewhat similar L by E. Microboon has the same L by E. And they can search for sterile neutrinos. So this is the probability, and this is the at microboon and Icarus. So they can look for the probabilities at different distances. They can do cross-section measurement, new physics searches. So microboon has started taking data since 2015, and their primary goal is to identify if the mini-boon low energy excess is due to the backgrounds or sterile neutrinos. Because of the excellent resolution of liquid argon detectors, they can separate electrons and photons. So the microboon results published last year, it said that they disfavor this neutral current background as origin of neutral current as the origin of the low energy excess, and they did not report any neutrino excess in data. So then how should we explain the LSND mini-boon results? So whether the new physics needs to be proposed. Now the current situation is that if one does a global fit, then it is still allowed. The electron neutrino excess cannot be excluded in the model independent way. That was shown by global fit, and the global fit still allows the 3+1 sterile neutrino picture. And if the SBN detector do not find a signal, then a lot of alternative explanations were proposed to explain the mini-boon low energy excess. And so we have to then think about how to test all these. Now, this brings me to the BSM physics at fixed target experiments. So we know that when we are doing the accelerator experiments, the proton beam is hitting the target and it is producing the neutrinos. However, it can also produce some dark matter, heavy neutral lepton, and a lot of studies have been done on this. So the dark matter detection in neutrino experiments is a very active field. It can come from indirect detection of dark matter, direct search for boosted dark matter, then direct search for sub-GeV dark matter in neutrino experiments. So the importance is that, the direct detection experiments cannot probe this sub-GeV region. So this is some result from the DUNE, where people have constrained the mass of dark matter from the DUNE experiment, and this red line is the DUNE result, and in the off-axis one gets, this prism is off-axis, one gets a better result because the background is less. And one can also constrain general U1 models from DUNE, because if you have an extra Z prime, one can have extra interactions. And we had done some study to show that we showed that DUNE gives a better constraint than other experiments in the context of such models. So this kind of studies in the context of DUNE is very important. Absolute neutrino mass can come from beta decay, neutrino-less double beta decay, also from cosmology. And this is the Katrine, this is tritium beta decay by Katrine. And the ongoing experiments, the present limit for Katrine is 0.8 electron volt, and the projected reach is 0.2 electron volt. So this, you can see, so this plot, this is the normal ordering, this is the inverted ordering, and this region is the degenerate. So already it differentiates between degenerate and hierarchical spectrum. So one has to come below this, to below this 0.2 EV, to distinguish between normal ordering and inverted ordering. And one needs new ideas. There are many ideas beyond Katrine. And this, because of the conference, I thought this is important to mention that this holmium reaction on holmium, they are planning to use quantum sensors. Chris had mentioned about Ptolemy, which can also detect relic neutrinos. So expect to reach neutrino mass sensitivity around 1 eV or less with this. There is also Project 8. Catherine can have other physics goals. It can search for relic neutrinos. They have given their first result doing a peak search. Also from the kink, they can search for sterile neutrinos. That also they have result have been published for Catherine, this data which they published in 2019. And they are also future planning for search for KV sterile neutrinos. So neutrinoless double beta decay tells whether neutrinos are Dirac or Majorana. And the half-life depends on this M beta beta or MEE, which is the effective neutrino mass, and the nuclear matrix element, which is the major uncertainty in this. This is the diagram. In the standard model, there can be extra diagrams in BSN, also like sign dileptons signature in collider from similar process. The neutrinoless double beta decay limit is here, current limit from different experiments. Now, ton scale experiments can, like Nexo or Legend using germanium or xenon, can confirm IH. And beyond ton scale, whether it's a question now, whether it can be reached or not to reach normal hierarchy, supposing there is no signal here. So that means inverted hierarchy is disfavored, but whether we can reach in normal hierarchy or not. But this is a problem because you need large mass, and then the enrichment is a problem. So certain nuclei are discussed for this, and I won't dwell on this slide, but this is a nice slide from this, which shows that which nucleus have what advantage. So if you are interested, you can take a look at your leisure. So this brings me to the last topic, which is neutrinos from astrophysical sources. We have observed solar neutrinos. We have observed neutrinos from SN 1987A. Then IceCube has found correlation between high energy neutrino and blazar for a tidal disruption event, active galaxy. This is very new. The paper came 4th November. And there can be a lot of physics which one can do using these high energy neutrinos. For the neutrinos, we can do neutrino interaction at high energies, probing flavor conversion at high energy, test of neutrino properties. And here also one can probe BSM in neutrino detectors, and one can of course study distant astrophysical sources. So there are many current and planned detectors. And this is a kind of, this shows at a ultra high energy, and this is a nice snapshot. So the main thing is to enhance the statistics and use different technology. So this is a snapshot of different detectors. And so these are proposed or under construction. And, there are also different detection like radio detection. IceCube was optical detection in ice. Then they have radio detection in ice. So there are various things which are coming in this direction. So we don't have any, even with all this, we don't know why neutrino masses are small. And that is the seesaw model remains to be the most popular model for this, which explains the small neutrino mass by tree level exchange of some heavy particle through the Weinberg operator. There can also be radiative masses. And seesaw says that there is violation of lepton number, so which requires Majorana natures of neutrinos. And there are many connections of seesaw with baryogenesis, dark matter in seesaw models, in Higgs vacuum stability, collider physics, etc. And for the neutrino mixing, we would like to know why 2 large and 1 small mixing angle, unlike quark sector. And here the main thing remains the flavor symmetry. And the precision measurements can help at least disfavoring some models, but there are many scenarios which can also be proposed. So this brings me to the end. So there is remarkable progress in past decade in unraveling oscillation parameters, and 3 flavor paradigm is well established. However, I would like to really emphasize this here, that neutrino physics does not mean only neutrino oscillation. There is much more to neutrino physics. There is a rich and diverse future program. Several experiments are proposed, new detection techniques, development of analysis tools. There is connection with nuclear physics, astrophysics, cosmology, BSM physics at neutrino detectors, both oscillation and non-oscillation. This is an emerging field. And I have not touched certain things because of lack of time, but thank you.
questions? There's some problem, but I think. Yes. The last slide showed something about
Yeah. Yeah. So see, if your delta CP is say -90, then the anarchy models are disfavored because they are predicting. But as you know, with models, one can again then change the model perhaps. And this was we did in 2016. I have not checked up on that. So are there some models which are giving low delta CP now? Okay. The earlier models were giving this high delta CP, this. Not for me. These are, sorry, I should explain. I have collected models of different people and I have taken their CP. So this paper was by Andre Diguvia. So I didn't put the list, Andre Diguvia et al. And they said anarchy was predicting plus 90 at that time, 2016, whatever papers we considered.
Komalis, these neutrino nuclear cross sections that you mentioned, that will depend, particularly for the charge current, depend on that particular nucleus involved also, right?
Yeah.
So basically carbon and lead will not have the same cross section.
True. Yeah.
So since you made a big deal about how neutrinos are more than oscillations.
Yes.
I was really struck with this precision measurement of sine square theta W. So how good will those measurements be? I mean, LEP has incredibly good measurement already. So how does the thing compare?
There are papers, as you know, I have not looked into that. There are sine square theta W measurement in coherent and dune, but I have not looked into those results. But I was saying not about the precision measurements.
No, it was just a curiosity.
Yeah, I don't remember exactly what error bar they are giving.
No, because also they will be impacted, similar to what Kamlesh said. They might be impacted by the strange quark content of the
uncertainty yes.
of the
so
nucleus.
Coherent analysis is there, dune analysis is there. That's
so it
how
would be
they are
interesting
doing
to know.
Yes,
since you are.
This
was something I didn't know till now. So that's why. Thanks.
Yeah.
This is vast literature now in that, Rohini, in all these.
Sterile neutrinos, as you said about, talked about the sub-electron volt, right? Sterile
Electron volt, yeah.
Sub-electron volt. So what about the heavy ones?
See, KV sterile neutrino, as I said, there are a lot of work on KV sterile neutrino because, as you know, KV sterile neutrino can be the dark matter candidate also. Now, Catherine experiment is saying that they can do some study on KV sterile neutrino, but they have to increase their detector, change their detector. So they propose something called a Tristan, which is some silicon drift detector. There is also another experiment which is BEAST. I did not put it because I couldn't read about it or there was no time to show. So that experiment is also for this KV sterile neutrino search. Also, there are bounds from astrophysics, supernova and those things, there are bounds.
Okay. Any more question? If not, let's thank Srubabati again.